Let's face the harsh reality of the Physics 9702 exams right off the bat. You can memorize every single formula in the entire syllabus, you can spend hours highlighting your textbook until it glows in the dark, and you can still completely fail to get the grade you actually deserve. Why? Well, because if you don't know how to structure your answers exactly the way the Cambridge examiner wants to see them, you are literally leaving easy marks on the table. Today, in this explainer, we're mastering crystal structure, and we're not just looking at it as some fascinating physics concept, but as a strategic precision tool to systematically extract every possible mark from your exam paper.
Solid because atoms are close. If you write this in your exam, you're getting 0 marks. That is the examiner's red pen instantly wiping out your hard work. It's a brutal, incredibly common mistake that students make right at the start of a paper. It's just a tiny, seemingly innocent sentence, right? But it instantly costs you easy marks and severely threatens your entire grade boundary before you've even properly warmed up.
So you might be wondering, why did this vague answer just cost you a grade boundary? It's pretty simple, actually. Ordinary revision fails because examiners aren't just looking for a random list of isolated facts. They absolutely demand that you connect microscopic order to macroscopic consequences. Saying atoms are close isn't physics, it's honestly just a guess. You have to prove exactly how invisible, microscopic atomic arrangements directly dictate the physical behaviors that we can actually see and measure. Section 1. The 4-step lattice framework. Okay, let's dive into this framework that will rescue your grade and systematically collect those crucial method marks. Step 1 begins with the foundation, which is the unit cell. A unit cell is a repeating pattern in 3 dimensions that acts as a compact rule for rebuilding an entire solid. I want you to stop thinking of this as merely some flat, boring diagram you memorize from a textbook. It's not. It is the fundamental mental blueprint for the entire material. Endless repetition of this exact, microscopic block builds the entire universe of a crystal solid. And this brilliantly illustrates what happens when we scale that microscopic blueprint up into the real world. Let's compare a crystalline solid with an amorphous one. Because a crystalline solid has long-range order, all thanks to that repeating unit cell, it fractures cleanly. On the flip side, an amorphous solid has no long-range order, so it softens gradually and behaves much less predictably. This immediately proves how long-range atomic order dictates measurable, macroscopic physical behaviors. Now, what's really interesting is exactly what the material inherits when that unit cell repeats endlessly. It dictates 4 exact features. We're talking symmetry, spacing, coordination, and bond geometry. When you explicitly mention these specific features in your exam, you are building the exact chain of reasoning that examiners reward. You aren't just giving a generic textbook definition of a crystal lattice, you are explaining how the lattice actually predicts material behavior. So, the absolutely crucial point here is that if you can speak through these 4 steps, you can conquer any structure question they throw at you. Always answer in this exact order. 1. State the definition of the structure. 2. Describe the microscopic cause, which is the repeating arrangement. 3. State the macroscopic consequence, meaning the key property that follows. And 4. Link it to a real application. Using this specific structure prevents vague answers and actively forces you into the top mark bands. But that brings up a pretty fascinating question. What happens when the exact same atoms are arranged differently? In a moment, I'm going to reveal a hidden examiner clue about carbon that changes literally everything you thought you knew about materials. But first, we need to put our framework to the test to make that clue totally obvious. Section 2. The 2-student duel, diamond versus graphite. All right, let's move to a head-to-head challenge. Here we have 2 forms of pure carbon. Take a second, maybe pause here, and predict which explanation is going to grab the top band marks from the examiner. Diamond has a 3D covalent network structure, and it's exceptionally hard. Graphite, made of the exact same carbon atoms, is a layered lattice, making it soft and slippery. Can you spot why these 2 forms of the exact same element behave so radically differently? Let's reveal the winner of the duel. The flawed answer says, diamond is hard because of strong bonds. Now, that sounds okay, but it's weak for A-level. The top band answer, however, states, diamond's 3D covalent network produces exceptional hardness, unlike graphite's layers. This is the examiner clue I promised you. It definitively proves that arrangement matters just as much as composition in your exam answers. The 3D structure is the actual microscopic cause of the macroscopic hardness. Section 3. Solving the impossible question. Okay, we're going to escalate the stakes now. What happens when the exam paper throws a massive curveball that seems entirely outside the normal bounds of a physics textbook? You turn the page and you see this genuinely scary past paper style question. Describe one engineering application where crystal structure matters and justify your choice. A lot of students just panic here. But I want to reassure you, this is actually an incredibly easy win if you simply fall back on our 4-step framework. You just need to provide that real application step. This is where we connect the microscopic lattice to high-stakes macroscopic engineering. Think about it. Semiconductor wafers rely entirely on controlled atomic order. Turbine materials and engineering alloys, they depend on structural regularity. Even gemstones display visible crystal symmetry. A learner who links crystal structure to microchips, wind turbines, and engineering steels will remember the physics so much better and obviously score higher than someone who just tries to blindly memorize terminology in isolation. Let's see how this builds when we look at specific lattice families. Face-centered cubic, or FCC, tells a whole story about highly efficient packing and slip planes that allow for ductility. Body-centered cubic tells a completely different story about spacing and mechanical rigidity. Simply mentioning these specific lattice families in your answer tells the examiner a highly sophisticated story about a material's mechanical behavior. So the crucial point to take away from this is this exact examiner-style correction. Always relate structural regularity to controlled imperfection in real-world materials. Advanced ceramics and engineering steels completely depend on this exact balance. This is the exact mindset shift that turns a vague list of random facts into a precise, top-tier exam justification that examiners absolutely love to read. Section 4, the grade-saving binge loop. So, we've successfully covered the definition, the microscopic cause, the macroscopic consequence, and the real application. But let's pivot for a second and do a quick countdown from your current grade to your target grade. Because even with the ultimate crystal framework, there is a catch. The missing pieces to getting full marks include command word awareness, timed answer writing systems, and links data analysis skills. I have to be completely honest with you here. Building this incredible mental framework of a unit cell is completely useless if you misinterpret the command words the examiner uses to ask the question. If they ask you to evaluate but you only describe, you will lose marks no matter how flawless your physics is. And that leaves us with this final, truly provocative thought. The final missing piece to your target grade is hidden in command word strategy. Do you truly deeply know the difference between explain, describe, and justify in the eyes of a Cambridge examiner? I demand you take the 4-step crystal framework we just built together and apply it to our next explainer focusing purely on command words. Mastering both is the absolute only way to guarantee your success. See you there.